Hello viewers, welcome to Quest, which is your weekly inter-school science quiz. I am Gaurav Gupta, back with you for yet another session of very interesting questions. Asking a lot of scientific questions here and conducting those experiments, we have Dr. Jayanto Sthanapathy. Please give him a big hand. Dr. Jayanto Sthanapathy is the director of National Council Science Museum's headquarters. And as you're already aware, Quest is a joint production between Doordarshan Kendra Kolkata and the National Council of Science Museums. Now, let us begin by introducing the teams to you. On my right is the J.C. Bose team. They are the boys from St. Xavier's College. They are?
I'm Shayan Das from St. Xavier's College, Kolkata.
I'm Shayantan Banerjee from St. Xavier's College, Kolkata.
I'm Arnav from St. Xavier's College, Kolkata.
Welcome to our show. And on my left are the boys from La Martiniere, and they are?
I'm Gaurav Khemka from La Martiniere Boys, Kolkata.
I'm Harsha Aditya Poddar from La Martiniere for Boys, Kolkata.
I'm Milind Banerjee from La Martiniere for Boys, Kolkata.
Welcome everybody to our show. Let me begin with explaining the rules of today's contest. Please remember that Quest is a weekly science quiz which is aimed more at education rather than a competition. In today's episode, we'll have 7 questions in all. The first 4 will be direct questions. 20 points for every correct answer, which is answered on a direct question, and 10 points for answers on passes. In the second part of the program, that's the last 3 questions. They'll be on the buzzer. Plus 20 if you get it right, minus 10 if you get it wrong. Remember, in the buzzer round, when you hit that buzzer, you must be ready with the answer, irrespective of whether the question be asked or not. Anyway, on now to the first question. The first question goes to the team seated on my right. That's the J.C. Bose team, the boys from St. Xavier's College. Dr. Sthanapathy.
I have a coil of wire here, and this coil is connected to an electric meter. The meter has a center 0 needle. Normally, it is at the center and it shows 0. Now, no battery is connected to this coil, so there is no deflection in the meter, right? Can you see it? Okay. Now I have a magnet. If I bring the magnet nearer to the coil, you find some deflection. If I push the magnet inside the coil and hold it, the meter shows 0. When I withdraw the magnet, it deflects in the other direction. Why this is happening?
First of all, when we are bringing the magnet inside that coil, we know there is some electromagnetic induction going right there.
Okay.
So, as we are giving some motion to the magnet, it is changing the magnetic flux in that. So, electric current is produced on that wire, and hence it is showing some deflection in the meter.
Right.
And so, when you place it inside and make it stationary,
yes.
So as there is no change in magnetic flux, so there is no current producing right there, and when you bring it back, then there is another further fraction of a second, there is a change of flux and it shows a deflection.
But when I am withdrawing the magnet, why the deflection is in the other direction?
Because you are trying to take it out from that.
Okay.
You're taking out from the circuit.
Do you know what law is called? Do you know this phenomenon is governed by which law?
It's electromagnetic induction and known as Lenge's law.
Okay, that's absolutely right.
Wonderful answer, J.C. Bose team. Dr. Sthanapathy, can you add further to that?
I want to add a few words to this. You see, the coil has no battery in it, and when there is magnet away from the coil, there is no deflection in the coil. When I bring the magnet nearer to the conductor, there is electromagnetic induction. And we know that whenever there is a relative motion, between a conductor and a magnet, there is induced current in the conductor. In this case, the conductor is the coil. Now, when I bring north pole nearer to the coil, there is induced current which will create north pole to oppose the cause. When I am withdrawing the magnet, the current is created in such a direction that it creates south pole and it attracts the north pole, and that is governed by Lenz's law. Okay.
So 20 points to you, 𝐺𝐶 team. La Martiniere boy, did you know the answer to that one?
Yeah.
Of course you did. Well, we'll wait to find out what happens in the next question. Welcome back, viewers. In the last experiment, Dr. Sthanapathy showed the boys from St. Xavier's College how to save on the electricity bills. Well, let's see what he shows the boys from La Martiniere. Your question.
I have a symmetrical double-ended cone in my hand, and in front of me there is a track which is divergent from the left-hand side to the right-hand side, and the left-hand side of the track is of less height than the right-hand side. Okay? If I release this cone here, it runs uphill. You are sure that the left-hand side is lower than the right-hand side in this track, but the object moves from lower end to the higher end. The question is why this is possible in this case.
Is it so because the center of mass of the double-ended cone,
Yes,
it always tends to get the mean position,
right.
and therefore it as the two ends are they are convergent and they end in a point, so the more it moves forward, the center of cone, the more it tends to get in the center position, and the more forward it tries to move.
You mean the CG position of the CG goes down in this object?
Yeah.
Okay? I think that's the right answer.
Well, good answer there, Gaurav. You get 20 points for your team. I think, Dr. Sthanapathy, you can add a little bit more to that.
Yes, I have to elaborate
Yep.
your answer. If you measure the left-hand side of the track, it is roughly 2.5 centimeters. And the right-hand side is roughly 4.5 centimeters. So definitely the right-hand side is higher than the left-hand side. Now, if you consider the cone, if you join the two ends of the cone by an imaginary line, the CG will line at the center of the line. Now, if you measure the height of this one end of the cone, here it is roughly 7 centimeters. When the cone is on the other end of the track, it is 5 centimeters. So, the cone actually is going down. It's not going up. But apparently it looks that the cone is going up. If you release a cylindrical object, then it will not happen. It won't go.
Right. So then 20 points apiece, and it also teaches you not to trust your eyes because things may not be what they seem to be. And we'll be back now with the next question. Welcome back. You're watching Quest, which is our weekly science quiz for students studying between classes 9 and 12. The teams here are the 𝐺𝐶 team. On my right, that's the boys from St. Xavier's College, and on my left, the C.V. Raman team. They're the boys from La Martiniere boys. As you saw, they've both gotten off to a flying start, 20 points apiece, and now before Dr. Sanapati goes ballistic, I'm going to get back from here. Yes, Dr. Sanapati.
In this box, I have kept an electronic oscillator. So if I switch on, it makes sound. And the frequency of the oscillator is fixed. That means it is not varying. Okay? Now, I'll give a whirling motion to this oscillator. Do you find any change?
Yeah.
There is a change in the frequency, in the frequency of the oscillator. And when it is stationary, it is having fixed frequency. Why this is happening?
We know a thing called Doppler effect.
Okay.
And we know that when the source comes near to the observer
Or the
listener, it always the intensity comes up, becomes higher and higher.
Intensity becomes
Or the
high.
frequency becomes higher.
Are you sure? Intensity or frequency?
No, because it's intensity, but frequency is steady. Frequency cannot go different.
Okay. Then
But the intensity has to be made higher because as it coming closer to me, so by the Doppler effect, it goes higher, and hence when it's going further, so intensity is going much below. Hence, when you're rotating or giving a whirling motion, so when it comes toward me, I have a much more sound sensing, and when it's going outside, it's a less.
I'm sorry, that's not the correct answer. So the question goes to
Here, as you whirl it, as it comes near us, the frequency changes because the tangential force, the velocity of the observer is the listener is constant, but the velocity of the source is changing.
Okay.
So there is a change in the frequency. N dash is equal to n v minus v0 by v minus vw. Here VW will be
okay, I'm not getting the correct answer.
Basically, it
Well,
is the
it's-
Doppler's effect.
Yes.
As it comes nearer, it is the frequency which increases. As by the
Frequency
formula
increases.
increases. Whereas
Yes.
as it goes away, it is the frequency which decreases. So
Right.
obviously, it becomes high
Right,
pitched and low
that's the
pitched.
correct answer. Absolutely correct.
I'm sure most of you will understand why I moved out of the way here. Dr. Sanapati, you must promise not to do that again unless you warn me in advance.
Yes.
I'll have to get myself a helmet.
Now,
Okay, good answer there, boys. As you know, in that question, you got that one on a pass, so you pick up 10 points there. But before we go any further, Dr. Sanapati will give you a much more detailed explanation.
now here is the oscillator, and I'm the listener. When I'm giving it a whirling motion, for some time it is away from me, and again it is coming back to me. So the source is coming to the listener, and it is going away from the listener. When the source is approaching the listener, the frequency increases. To the listener, apparently, not the original frequency of the oscillator is increasing, but to the listener, the frequency increases. And while it goes away from me, from the listener, the frequency is reduced. And that's why you listen to a variation in the frequency when this is in motion. That's the right answer.
Minus 10 to me, okay. Thank you, Dr. Sanapati. That was a very nice and detailed explanation. Boys from La Martiniere, that is the C.V. Raman team, you pick up a bonus 10 points. You move on to 30 points. And the next direct question is for you. Welcome back to Quest. This brings us now to the last of our direct questions. The scores first. C.V. Raman team, 30 points. J.C. Bose, 20. Next question for C.V. Raman team.
This experiment has two steps. I have mercuric chloride in my left hand in a test tube, and I am adding potassium iodide to this. We get a precipitate which is orange in color. Okay? Now I am going to add excess potassium iodide in it. See, the precipitate gets dissolved. My question is, what was the red precipitate? And secondly, when it got dissolved, what compound is produced?
𝐺𝐶-BOS team, I suggest you also discuss this quickly. Please hurry up, CV Raman team.
Excess of?
Yeah.
Please repeat that.
Potassium iodide.
Potassium iodide, that's right.
Okay, first say this.
We have another 5 seconds for you.
Okay, the red precipitate was mercuric iodide,
Okay, that's correct.
and this is complex salt.
Yes.
The potassium
Iodide.
mercurous iodide.
Mercuroiodide.
Mercuroiodide.
Potassium mercuric iodide.
Iodide.
I give them full marks.
Well done. Let's give them a big hand.
Very good.
Dr. Sanapati.
Yes. The red precipitate was mercuric iodide, and when I added excess potassium iodide, a coordination complex was formed, which is potassium mercuric iodide, and this is soluble in water.
Well done then, CV Raman team. You got your direct question absolutely correct. You move on to 50 points, and you shot well into the lead, which now brings us into the buzzer round. Welcome back to Quest. 50 points to the CV Raman team, 20 to 𝐺𝐶-BOS. Let's see what happens in the next one, which is the buzzer round. And now, on to breakfast with Dr. Stanapati.
I have 2 eggs with me. One is raw and the other one is boiled. You have to tell me which one is raw, but without breaking it or without touching it. And you have to tell me how can I find it out.
Okay, 𝐺𝐶-BOS team.
The first thing, as you have said, the thing on your right hand is raw, while on the left hand it is
No, I didn't say. I
No,
said
no.
one is raw and one is boiled.
boiled. So just to say which one is
Okay,
raw.
let us consider.
Okay, let us consider the left one is boiled and the right one is raw.
Right.
And now if we just put it in the salted water.
No, you are not allowed to bring in anything other than this table and the hands.
Sorry, you cannot taste the egg at this stage.
Okay.
Yeah.
I got it.
You have to instruct me what I have to do with these 2
Okay.
eggs.
If we just give it a rotation,
Okay?
now then the raw egg will stand up, or like it will rotate on the axis of rotation, and it will be more or less straight.
Okay.
Well, when you rotate the boiled egg, as the point of application is much more and the friction is much more, it will stay at that position. And when you go it for, as we know, the point of application of rotation has to be minimum for rotation, then it would stand up.
You mean to say I have to give it a
No,
spin
no.
like this?
No, no, just,
Like this?
yeah.
And it will stand up?
It will stand up.
If it is raw?
It is raw.
Okay. Do you have any other answer?
Is there, you want to ask them first, Dr. Sanapati?
No.
Okay, let us
This was
try.
there, yes, it was there.
Sorry, Rick.
If they, you have to go to the audience.
You want me to spin this?
Yeah. With a much more velocity.
Much more?
Oh God.
No.
Okay. And the next one? So that one is, yeah, that
That
one
one
is
is what?
Boiled egg.
This one is, no, that one is raw. That one is boiled, and
This one is boiled in
and
my
this,
left hand,
yeah,
and this is raw.
raw.
But I'm not satisfied with your
Because
explanation.
I was just in the wrong side, because as it's hard and it's covered, so it's a total solid piece of mass.
Okay.
While this is having some liquid inside it,
Yes.
so mainly it has a viscous effect. So
I'll go to the audience for a better answer.
I'm sorry, 𝐺𝐶 team, you kind of scrambled and overcooked your answer here. Do we have any answers in the audience? Who should I ask? I think I'll ask you to come up. Yes, please come. What's your name?
Somendu Das from 𝐾𝐞
Can you add to that? Yes.
Without breaking it.
Okay, sir.
Just tell him what to do.
So first of all, we spin both the eggs
Okay.
together.
Together. Fine.
Now we tap each one once with our hands.
Yes.
Then we will see that the one which is boiled will stop immediately,
Okay.
and the other one will still spin. That is because of inertia. The liquid inside the raw egg will still continue in motion. Will be in motion. Still, it will be in motion, and the thing which is boiled, the egg which is boiled, will stop.
Okay, that's the absolutely correct answer.
Great answer there, Shomendu. Here's a small memento for you from Quest. Thank you for coming.
Suppose this is the raw egg, and I give it a spin. Let me try it once again. No?
Gentle tap.
Gentle tap, but it doesn't stop, because the fluid is in motion inside the egg. And if this is the boiled egg, it immediately stops. It stops.
Thank you. So 𝐺𝐶 team, you end up with -10 there for hitting the buzzer wrongly. The scores at this stage, 50 points to the CV Raman team, and 𝐺𝐶 team, you're down to 10. Buck up, boys, you better do well in the next two. Welcome back, viewers. Second of the buzzer questions, over to Dr. Sanapati.
I have some liquid in this glass, and I'm pouring this liquid inside the conical flask and closing it with the cork.
I can't look. Shut your ears.
Okay, tell me why the balloon inflates.
Okay.
Yes.
I know.
Oh, you have
𝐺𝐶
pressed.
team.
The liquid in that glass was liquid nitrogen,
Okay,
and we know it has a very low boiling point. So when you pour it in the normal temperature, it quickly starts to evaporate, and hence when you have putting something inside, as the tube is fitted with the balloon, so the gas goes inside as it inflates.
that's right. Very good answer.
Good answer, 𝐺𝐶 team. You pick up 20 points there. I'm sure you don't want the balloon,
No, I think so.
but Dr. Sanapati will give you a more detailed answer.
See, the room temperature is around 300 degree Kelvin.
Kelvin.
And the temperature of the liquid nitrogen is 77 degree Kelvin.
Kelvin.
So when you pour liquid in the conical flask, the liquid expands immediately and forms nitrogen gas, and which inflates the balloon. That's the correct answer, and you have given the right answer.
So 𝐨𝐳-𝐲𝐬 team on the comeback trail. 30 points to them, 50 to C.V. Raman. On to the very last of these experiments.
On this card, there is a painting of a parrot.
Okay, C.V. Raman team.
And on the reverse, no?
We shall wait for an answer from them. Dr. Sthanapathy, I trust you will not change the question halfway. Come on, boys.
Okay.
What's the answer?
We will continue to rotate that card very, very fast.
Okay.
Now the human eye senses things, the change should be 0.1 second. Now because it's going about rotating so fast, the human eye will think that the parrot is inside the cage, because our eye sense only at 0.1 second, whereas it's rotating at a much faster rate. So it seems to us as if the parrot is inside the cage.
It's an optical illusion.
It's an optical illusion of a kind.
Are you sure this is an optical illusion?
Yes.
Okay, I'll go to the audience for a better answer.
Okay, any answers in the audience? I think, all right, why don't you come up? What's your name?
I'm Sheikh Wasim Raja from St. Xavier's College, Kolkata. Yes, when we're rotating this, and we know when some vision comes to our eyes, it takes about 0.1 second to be resolved in our brain. When we are rotating it very fast, it changes, it alternates before 0.1 second has been gone. So when within this period, within this 0.1 second, two visions are coming in the same position, they are superposed in our brain.
Superimposed?
And, yes, superimposed in our brain. And we looked at the parrot is inside the cage.
That is correct answer, but the answer which the La Martiniere boys have given, that is also correct. So I give them marks.
Okay. But for getting the answer right, we have a small memento for you. Well done. Thank you. So you do finally pick up those 20 points, but before we go any further, Dr. Sthanapathy will now ask the question. Yes, Dr. Sthanapathy.
Yeah, the question you have already answered. You know, this is due to persistence of vision and not due to optical illusion.
That brings us to the end of today's edition of Quest. The final scores, C.V. Raman team 70 points and the 𝐨𝐳-𝐲𝐬 team 30 points. Well done. We have a small memento for you from Quest. Let's have a big hand for them.
Thank you, sir.
Better luck next time, 𝐨𝐳-𝐲𝐬. Coming to you. We'll see you again with another edition of Quest next week at the same time. Till then, it's goodbye.